Hello students, and welcome to section 7-2, Inverse Functions and Relations. Find inverses. So an inverse relation, as it's described here, is when two relations are inverses if and only if, whenever one relation contains the element a comma b, the other relation contains the element b comma a. We should probably reflect a little bit upon what a relation is in the first place. A relation is something where, for example, a linear function, it's a more specific version of a relation. However, a linear function compares two variables x and y. For example, y equals mx plus b, you're comparing x and y. X and y are related as such. Now, it doesn't have to be a function in order for it to be a relation. You could have something like, for example, the equation of a circle. If you recall a generic equation of a circle, x squared plus y squared equals r squared, something to that effect would be a relation because it still compares x and y. It's just not a function. When we're comparing two variables, x and y, or as they're saying, a and b, inverses speak to the idea where you switch x and y, or a and b, in context. Property of inverse functions, more specifically, again, the difference between a relation and a function is that a relation just compares two variables x and y, while a function is more specific to, for example, one of the easiest ways to remember that it is a function is that it will pass the vertical line test. A relation is a function if that's the case. Suppose f and f inverse, that notation as it looks to be a -1 exponent, is called the inverse. So these are inverses of each other, and they're inverse functions. Then f of a, so if you plug in a into the f, it will equal b. So a comma b, think of it as. If and only if with the inverse function, so f looks again to be a -1 as an exponent, f inverse of b is equal to a. So if you plug in a into the f function, you get b, and if you plug in b into the inverse function, you get a. So it would be b comma a. All right, let's dig into this a little bit more. I do have, as before, an example that I can uncover here for you. It says find the inverse of the function f of x equals 2/5 x minus 1/5, and then graph it and its inverse. Okay, so as I uncover things here, I want you to take a look, and I have some steps as usual. Okay, I'm going to go ahead and uncover, see what I can maybe do without uncovering too much here. So as I continue, we're going to start with, and I can show, let's do this. We can go this direction. And I think that's more conducive to what we want to do, but the graph will start to unfold as well. Step one, replace f of x with y in the original equation. So the original equation is simply a line. Think of it again as y equals mx plus b. If I call this y instead of f of x, here's what it looks like. Okay, so please note that y equals 2/5 x minus 1/5. And as we continue down, step two is to interchange x and y. Quite literally, you're going to take the equation you just wrote here, and you're going to flip or interchange x and y. So now instead of y equals 2/5 x minus 1/5, it's x equals 2/5 y minus 1/5. Next, step three, solve for y. And as a matter of fact, before I solve for y, I would like you to take a look at this, this graph. So the equation y equals 2/5 x minus 1/5 is right here as they've pointed to. Okay, now we're about to see the inverse take shape as an equation, but that's technically the graph of the inverse. We're going to talk about something called the axis of symmetry. We're also going to be taking a look at the xy table, not just for f of x, but also f inverse of x. Okay, let's talk about after maybe we see how y is solved for. To solve for y, as you can see, it's very much what you would expect in this equation again, multiplying both sides by 5, which makes it very nice to work with now, where 5x equals 2y minus 1. does say multiply each side by 5, which is what I did. And then, as you can see, of course, add 1 to both sides. So here you go, 5x plus 1 equals 2y. And then divide both sides by 2. So 1/2 times the quantity 5x plus 1. Or if you distribute, y equals, or f inverse of x equals 1/2 times 5, which is 5/2 x. They actually left it as such. I wrote it here simplified. And then 1/2 times 1, which again they wrote here as a half. So y equals, or f inverse of x equals 5/2 x plus 1/2. So let's reflect back upon the graph again. Like I said earlier, this is the line that represents the f of x function, and this is the line that represents the f inverse of x function. The really neat thing about inverses is that you're always going to see, when you graph both lines, of course, you're going to see that there is this quote unquote, okay, this is my language, by the way, not the book's language, quote unquote, an axis of symmetry. I like to call it an axis of symmetry simply because the line is y equals x, as you can see here, because what you do have are points on either side of that axis that are quote unquote symmetric to each other. I'll explain. Let's pick the y-intercept on the f function, which is an easy point to start with. 0, negative 1/5, which is about right there. Remember we said earlier, when you take a comma b on the f function, it's simply b comma a on the f inverse of x function, or denoting it here as such. Because they are inverses, you can switch a and b, or x and y, as we did anyways on step 2, which is quite interesting. Watch. 0, like I said, negative 1/5. Well, what if you plugged in negative 1/5 into the inverse function? Negative 1/5 right here should in fact yield 0. So if you look at the graph, this line right here, which again is the inverse, will have this point right here as again what we described as a and b flipping. So negative 1/5 comma 0. Similarly, let's maybe look at another point here. How about 1 comma 1/5, which is right about here. 1 comma 1/5. Okay, notice if you were to in fact switch 1 and 1/5 such that it's 1/5 comma 1, 1/5 comma 1 on the other function, right, the inverse, is about right there. 1/5 comma 1. Okay, I'm kind of highlighting it with the top of my my cursor here. Okay, so this is a nice depiction of inverse functions, and again, the XY table is very nice to kind of go back to and and see if it makes sense in the sense of, again, switching x and y. Okay, let's move on. We're going to go ahead and find the inverse and then graph. For problem number 1, the equation is f of x equals 2/3 x minus 1. Okay, so I'm going to uncover. Let's see, do that a little bit differently. Sorry, uncover. So to start with, I actually I'm going to uncover my XY table because, as it turns out, it really won't be that much different than the last problem, in the sense where, noting this is the XY table, and I did pick some arbitrary x's and y's. I think picking 0 makes the most sense for sure, but -3, +3, when I plug in those values, it's going to make my y's end up a little bit nicer to deal with. You don't have to pick those necessarily, nor do you have to even pick 3 points. I would certainly pick 2 points minimally so that you can actually graph your line. Okay, those 3 points are fair. Keep that in mind as you're graphing and analyzing. Speaking of which, okay, I'm going to uncover everything at this point. I don't think I can without losing what I'm looking at for number 3, of course. Anyways, here's the equation of the original problem. So again, replace f of x with y. Next, switch or interchange x and y. So now it's x equals 2/3 y minus 1. Now remember earlier I had shown you the XY table right off the bat. If you think of how the inverse will unfold, think of how simply switching x and y, or a and b if you prefer, remembering the beginning of the lesson. So -3 is the same here as you see, so it looks to be probably the point of which the lines are intersecting, the graph of f of x and f inverse of x, which we'll find here in a moment. 0, -1 switches such that it's -1, 0. 3, 1 switches, so it's then 1, 3. So you can actually graph f of x and its inverse, f inverse of x, really just by virtue of the xy tables. And you should actually see that nice symmetry with the line y equals x as your quote-unquote axis of symmetry. All right, let me finish the problem and actually finding the inverse now. If you take this equation, multiply both sides by 3, which is what I did here. Okay, so you then have 3x plus 3, if you distribute, equals 2y. And then divide both sides by 2. You can actually multiply by a half and of course still get this same result. So this is the equation of the inverse, and it is certainly the same equation, or pardon, the same, it is the equation technically of this same line that I've already drawn in green. Again, thanks to the XY table that will really help frame your understanding. I'm going to ask that you try number 3 on your own. I will uncover this for your later analysis and comparison. But go ahead and try number 3 on your own. Let's move on to verifying. So inverse functions, two functions f of x and g of x are inverse functions if and only if f of g of x, here's another way to write that of course, is equal to x. And I circled x here because that's very important in the context of composition of both. Speaking of which, you'll also need to compose g of f of x. So g of f of x. We did talk about composition of functions in the last section, if you recall. So please reflect upon that as you proceed with this idea. So inverses and verifying inverses. So here are your functions. You've got f of x, which is 2x minus 7, g of x, which is 1/2 quantity x plus 7. So what we're going to do, and I actually, as you can see, I attempted to erase or kind of modify this. I'm going to actually just show you because I can squeeze in a 1 and a 7 for my numerators there. My expressions for that function, or the expression I should say for that function, looks like that. The g of x is simply 1/2 x plus 7/2 simplified. Okay, so we're going to compose f of g of x, and we're going to compose g of f of x as it describes here. Our goal is to get x in both cases. Let's see. So for the first, if we compose, I can do it like this. I'll show both at the same time. F of, again, this quantity, we're substituting this in for x here. So f of 1/2 quantity x plus 7, which again looks like this simplified. And then similarly, g of f of x, we can plug in 2x minus 7 there for x. As you can see, I'm set up and ready to go. In the next step, there's a lot that's about to happen here. In other words, literally plugging 1/2 quantity x plus 7 in for x, you've got 2 times that quantity, and then again minus 7. Similarly, if we're plugging in 2x minus 7 here, you've got 1/2 times that quantity, 2x minus 7, and then plus 7. Some really nice things are about to unfold. If you multiply 2 times this quantity, these cancel, so you're just left with x plus 7 minus 7. Here, if you distribute, after you maybe subtract 7 and negative 7, you'll have 1/2 times 2, which is again going to cancel. And that's quite nice because as you see here in the next step, 7 minus 7 in fact is 0. And here, well, 1/2 times 2 we already said is 1, or cancels as such. So x is the result there, and x is the result there. So the conclusion from the very beginning again, such that we're trying to see if they were inverses, the conclusion is the functions are inverses, since both f of g of x and g of f of x are equal to x. I do ask that you try example 2 on your own. Uncover or take a look at, the full-fledged answer. I will uncover it for you for later comparison.